The key to these three questions is Little's Law. I'll prove it to you. An item arrives for processing at an average rate of 200 items an hour, lambda, where each item spends an average of 30 hours, W, being processed. On average, how many items are in the processing system? To answer that question, how many items are in the system, we need Little's Law, which is a really simple formula. The number of items in the system, basically this that I underlined in yellow, that would be capital I, and it's lambda times W. Oh, right, that's why that was actually in the problem. What is lambda? It's, Little's Law, actually, what is it? It is the number of items that are hanging around is generally how fast items are arriving times how long on average they happened to spend in the system. So in our case, the only thing that you actually need to do to finish this question is you just need the parts for the formula. Average rate of 200 an hour, that is lambda, that's the arrival rate, 200 per hour. And the weight in the system, you know how long it takes an item generally to get through the system, 30 hours. The average number of items in the system is just 200 times 30. So it's, wow, 6,000 items. Yes, if they're arriving 200 in an hour, but they're going to hang around for 30 hours, each one of them, then on average you have about 6,000 of them hanging around. Okay, now, next question looks really similar. Looks almost like copy-paste. An item arrives for processing at an average rate of 200 an hour. Yeah, we're just looking at that, right? Where each item spends an average of 30 minutes. Okay, W equals 30 minutes. On average, how many items are in the processing system? That is the same question. It's the same formula. But what this question is trying to demonstrate is Little's Law. The formula is really, really simple. There is one thing to pay attention to. Whatever the arrival rate's talking about, like so many per hour or so many per minute, make sure that the lambda is talking about the same time unit as the W. In this case, you don't want to say 200 times 30. We would get the same answer as last time, and that doesn't make any sense. They're talking about two different time units, hours and minutes. No problem, just adjust one of them or the other. In this case, the easiest thing to do would be to adjust the W, so to speak. Okay, what is 30 minutes? It is how many hours? 30 minutes is 1/2 of an hour. Perfect. Then it's this number and that number that I want to put in here. So the answer to the question is the same 200 for the arrival rate times 1/2 or 100 items. Oh, so all of a sudden, right, it was almost the same question. One little word in there was changed, and the correct answer goes from 6,000 for the first question down to 100 for the second question. Why is that? Because if you look at it, there's a big difference between hanging around for 30 hours and hanging around for a half hour, right? This is a system that's moving things out the door faster. Now, third question must be related to this. Does look almost the same. An item arrives for processing at an average rate of 100 an hour per hour. And each item spends an average of 30 minutes. It's that same little twist. 30 minutes equals 1/2 hour. On average, how many items are being processed, or how many items are in the system if you just go in there and look. So now we're saying 100 times 1/2 or 50 items. How does that answer relate to the answer we got before? Because these two, the second and the third question, are the ones that are the most similar. Oh, right. The weight in the system is the same in both of them, but the average number of items that is sitting around at any given moment has dropped by half when you get to the last question, because it was the arrival rate, how fast that items were arriving, that had been reduced between the two questions.